Okay, welcome back to the Fall 2021 Hottest Seminar Series. This week's speaker is Kristina Sojakova from INRIA Paris, who will speak about Syllepsis in HoTT.
Thank you, Carlo. Thank you for everybody for inviting me to this fall seminar. And so I'm going to be talking about how to prove Syllepsis in homotopy type theory. And this is a problem that I wasn't even aware of a year ago, but it has been brought to my attention by Jamie Vickery and Ali Kaglan. Jamie gave a talk at, I believe, one of the seminars, maybe last December, where he was talking about, where he mentioned this problem among others. So as we know, well, probably I don't have to introduce what homotopy type theory is here. Whew, that's a relief here. So we know that the Eckmann-Hilton argument holds in homotopy type theory, namely if we have any two loops that are based on an identity, then they commute. And there are several proofs. At least I know maybe about 3 or maybe even 4 different ones. One, I think, mimics the actual mathematical argument in the non-homotopy type theory setting, and then there are various others that, you know, everybody came up with their own favorite proof. Favonia, Dan, Mike, and probably some other people. And I'm gonna be talking about yet another such proof. And as Noah Snyder pointed out, all of these are actually homotopic to each other, and it's fairly hard to just come up with a proof off the bat that isn't homotopic to one of these. But the proof I will show you has certain computational properties that make it suitable for proving Syllepsis. Now, Syllepsis, that was proved by me, and I think Egbert made significant progress on that problem too, says that if we go 1 dimension higher and we have actually 3 loops, well, we have 3 loops P and Q that are based at the reflexivity path on another reflexivity, then the Eckmann-Hilton proof that Q and P commute is in fact the inverse of the Eckmann-Hilton proof that P and Q commute. So as we will see, this is yeah, so there is I think Egbert was trying to somehow encode a mathematical argument that would prove this, but it turns out that if one just discards mathematical intuition and uses just path induction, then it turns out to be a lot simpler. And this happens to be the case. It turns out to be the case with several other things, several other arguments, I think, that are, you know, much simpler in plain homotopy type theory than in math, in my opinion. So yeah, so just to point out that these results are basically as good as it gets, because Eckmann-Hilton doesn't hold for 1 dimensional, for just plain loops, and Syllepsis does not hold actually if P and Q are 2 loops. We will see later where we need the fact that P and Q are actually 3 loops. Okay, so I'm going to start with some preliminaries that we all know, but since we will be talking about terms and how they go together, and we will be proving a higher coherence theorem about them, it's important to give them some names so that we know what we're actually talking about. So one important term that we will be using, and that is actually part of the Eckmann-Hilton proof itself, is the whiskering. So we have obviously whiskering on the left, where we keep the left path unchanged, and we perform a two-path transformation from X to Y on the right. And then we have the analogous whiskering on the right, where the right path stays unchanged. And the important result here is that these operations actually commute as long as they are performed on opposite sides. So whiskering on the left followed by whiskering on the right is actually the same thing as whiskering, the appropriate whiskering on the right followed by whiskering on the left, which sort of makes sense because we don't, if we leave one part unchanged and then we change the other part, then, you know, it makes sense that these should be interchangeable. So this is obviously very easy to prove by induction. And we should remember this term because it will be one part of our Eckmann-Hilton path. Okay, so yeah, so just to recap, so this this allows us to switch the left and right sides of the whiskering, and now we remember that concatenation on the left by reflexivity or the identity path is actually natural, as is any other operation in homotopy type theory. So in particular, whiskering on the left can be explicitly described if, as long as the left part is the identity path, then it can be explicitly described as discarding the identity path via this term. This syntax is supposed to mean concatenation, that's what the square is for, by one on the left. So if somebody has some better idea, then that would be great. But yeah, so so if we discard the reflexivity paths and then we just perform the plain old P that we started with, and that's the same as the whiskering. But of course, this is only in the case that we have the identity path here. But what does it mean in our case when P is actually based at an identity? So U and V are both identities. So then these terms obviously are definitionally reflexivities. So then what this says in effect is that the whiskering here is actually equal to the original path P. And that's, well, we have the entirely analogous situation here for Q and whiskering on the right. And that's why we get the Eckmann-Hilton path from. So we start with P and Q, and then by what we just proved, the whiskering on the left by the identity path is just P, and whiskering on the right by Q is just Q, right? And by the exchange law, we can swap these around, and then we do the same thing again. We turn this whiskering to a Q, and we turn this whiskering to a P. So now the question is, why is this proof particularly suitable for the proof of Syllepsis? And the answer is that if we look at this middle part, there's nothing, the exchange law that we have up here actually doesn't rely on anything having to be the identity. I mean, we see that the hypothesis say nothing about anything being fixed. We have just arbitrary points everywhere. So going back here, I mean, this path and this path obviously type check only because Q is in fact based at Q and P are in fact based at identities, but this middle part says nothing about, you know, the one is just in this particular case. And that's how we will actually prove Syllepsis, because this middle part will allow us to carry out a suitable generalization and the corresponding path induction. Okay, so now since we are proving something about the Eckmann-Hilton proof, we will need to know how it behaves, some basic properties. So the first thing that we would like to know, and that we will need to know, is what it does when one of the paths is a reflexivity. So in this case, there's an obvious manual way of going from the reflexivity concatenated with Q to Q concatenated with the reflexivity. Namely, we just discard the one and then reintroduce it on the other side. And the same thing in the symmetrical case. So why is this in fact the case? Well, this requires maybe about, I'm not going to show the code since Steve doesn't like it, but I think it requires maybe about 10 lines of code or something of this sort. And the most complicated lines are the ones stating the things to actually prove. Everything else is just induction. So, but intuitively, if we just eyeball this path, why is this true? Well, if let's say P is the identity, right? So then if we go here, then we're basically just ignoring the identity part. And then it's very easy to see that the Whiskering Exchange Law is defined by identities. So it's by path induction on P and Q. So basically, it's very easy to see that in this case, there is again an obvious manual thing to do. We discard this one and we reintroduce it on the other side. And then here, we again perform the same transformation, except in the opposite direction. So we go from the whiskering of Q to Q itself. So we accomplish precisely nothing because here we perform the transformation, we mess around with the identities a bit, and then we have undone it. So actually all we accomplished was to shuffle the one around, which is exactly what we claim here. Okay, so now the other thing we would like to know is the naturality of the Eckmann-Hilton proof itself. So if we go one dimension higher and we have some transformation in mind, some higher path Q from U to V, then we actually have a commutative diagram which says that if we turn U to V via whiskering on the right, and then we swap those paths around using the Eckmann-Hilton term, and that's the same thing as if we swapped it to begin with, and then we perform the same transformation, but now on the other side, on the right. So this is again very obviously true, and we have the opposite, the symmetrical case, where we're turning whiskering on the left, followed by the Eckmann-Hilton term, and turning it into an Eckmann-Hilton term, followed by whiskering on the right. So again, this will be important later, but now the question is, again, we remember that we're in this special setting where all of this, like U, X, and Y, are all identities, right? So in particular, the horizontal paths here are identities. So in this case, we see that there's, again, a more explicit way of constructing this. So we remember that we have this whiskering on the right, and we have whiskering on the left. And then these guys, that's just a more complicated way of saying this is just an identity. And likewise, this is just an identity. And we remember that this is the naturality of the concatenation on the right, and this is the naturality of the concatenation on the left. So basically, the naturality can be explicitly described as we first turn the whiskering on the right to Q, and then we turn it into whiskering on the left. So why is this somehow a better way to think about it? Well, it's not. We actually mean to go the other way, in the sense that if we have something like this, which we will have, as we will see in a bit, then we want to actually call it the naturality of Eckmann-Hilton. So we take this more explicit setting and we will turn it into the more abstract setting. more abstract term. And why is that better? Well, it's better because in order to even form this term, we need to rely on the fact that some of these paths are identities. So for example, here we're doing concatenation on the right by one, and that only makes sense if, you know, the thing is actually one. Whereas if we're talking about the naturality of Eckmann-Hilton, then there is no, we don't impose that any of these paths, u, x, or y, have to be actually identities. So P now in particular has two free endpoints, so we will be able to perform induction on it. So now, so again, this is what will come up in the diagram, and we will want to turn it into this in some sense. So, okay, so this is all we needed to know about the proof of the Eckmann-Hilton property. And now we can finally get to Syllepsis and its proof. So this is a formal statement of what we actually want to prove. And we can formulate this pictorially as follows. So we remember how we defined our Eckmann-Hilton term. So we take P and Q, we turn P into a whiskering, we turn Q into a whiskering, then we apply the Whiskering Exchange Law, and then we undo all of that to get Q and composed with P. And then, of course, this is the same thing, but in the other order. So we want to prove that this diagram commutes. And now the obvious thing to do is to split it, right? So we have a square, this square, and we have these triangles. And now we hopefully, if we somehow manage to prove that each of these parts commutes, then this will be the commutativity of the entire thing. So, and as we see, we are kind of in a good position to do so, because this thing, the Whiskering Exchange Law, was defined entirely by induction and doesn't rely on anything being the identity here. So it looks like we should be able to somehow apply path induction there. But the situation is a little bit more tricky. So again, how do we, in order to split the diagram the way we wish to split it in the obvious way, we somehow have to come up with these mediating edges here. And so we remember that our goal is to introduce a suitable generalization. So we want to do things by path induction, so it would be best. Here we have the ones in here, but it would be best if we actually manage to replace P and Q by arbitrary paths that go from P goes from X to Y and Q from U to V, and these would be just, you know, arbitrary two loops. So we could do that. We could replace P with this more general P and Q with this more general Q, and now the ones with the appropriate endpoints. But the problem there is that the endpoints don't match. The endpoints of the vertices of the square don't have matching endpoints, because this one thing, the top left thing, goes from U composed with X to, it goes from U composed with X to U composed with Y. To V composed with Y. And this thing goes from X composed with U to Y composed with V. So basically, the endpoints are almost the same, except the paths are concatenated in the opposite order. So what we need to do is we need to insert an Eckmann-Hilton term there to make sure that we are actually talking about the right order of paths. So now the diagram is going to get really big. So I'm going to switch to a more user-friendly, at least for me, setup. So Carlo, does this have to be enlarged, or is this?
Well, it doesn't look like you can make it that much larger, so it seems okay for me. Yeah.
Not, but maybe, okay, maybe this is better. No?
Yeah, it's better.
Okay. Okay,
Yeah.
so now we remember where we were. Okay, so our latest idea was to insert an Eckmann-Hilton term. So we remember that here we go from U composed with X to V composed with Y. So then we flip the V and Y. And here we also likewise flip the thing. And now we can finally talk about a square, right? So, okay, so now at least we have the vertices, and now we want the edges. So obviously the vertical parts are just the thing we had, except now they completely ignore the Eckmann-Hilton term there. This is just the parallel composition of paths. Okay, and so how do we construct the edges there? Well, let me go to the talk again. Okay, so we remember that we need to go from whiskering on the left, whiskering on the right, and the Eckmann-Hilton to Eckmann-Hilton, whiskering on the right, and whiskering on the left. So the obvious thing to do is, again, split it. And then we would like to just prove that each of these small squares commutes. But that is just the naturality of Eckmann-Hilton. So we're basically just composing two Eckmann-Hilton naturality proofs. The first one is the naturality on the left naturality, because we're keeping the left part unchanged. And then we have the right naturality. Yeah, so now we have constructed the edges. So this is the first edge. So one edge consists of these two squares pasted together. And the second edge is the same thing, but now we're doing the right naturality composed with the left naturality. So again, let's look at what that gives us. Wait, I didn't want to do this. Okay, I just wanted to do this. Okay. Okay, yes. So, yeah, where are we? Okay, so here we have the vertices, and now we just describe how to construct the edges. So let's go down here, and now we have the horizontal edges. So we have this composition. We paste together, we glue together these squares of the right naturality with respect to P and the left naturality of Eckmann-Hilton. And here on the bottom, we have the analogous thing, but first the left naturality and then the right naturality. Okay, so now why does this commute? Well, that is obvious because P and Q are now, as we remember from our slides, P and Q are completely arbitrary three loop. Well, they're not even loops anymore. They're three paths. So basically, we can just kill the whole diagram by path induction on P and Q, and everything is going to be reflexivity. So that's pretty good. And now let's substitute the actual endpoints into the picture. So we have basically the same picture as above, but now we have these ones here. And the interesting thing is that now the Eckmann-Hilton terms just become ones. because, all the two loops are actually ones. So, okay, so we have something that, if we look at what we wanted, so we wanted something that looks like this, and then we got something that looks almost like that, except it has these spurious ones lying around. But that's okay, because they're just reflexivities, so we don't really care about that. So we're just saying that basically we have a square. So what do we do next? Well, this was step 1. And then we have step 2. Oh yeah, maybe I wanted to mention one thing. Oh no, maybe I'll mention it later. Okay, so what do we do with this? So we would like to somehow, if we remember, we had these triangles. So let's say this middle square commutes, if we insert the ones in there. Okay, so the middle square commutes. And then how about the triangles? So the triangles should also commute. And they do, fortunately. And why do they? Well, let's take this path. Let's focus on the upper one. The lower one is symmetric. So we take this path, and yes, so again, there are these extra ones. So let's say we get rid of them via some, I just use this double arrows going down to indicate that we're just getting rid of the spurious paths. But for the purposes of the talk, we can just pretend it's not even there. Okay, so we just have this whole thing that goes from the vertices we originally had in our diagram. And now we have P and Q up here. And our original paths that are part of the Eckmann-Hilton term, namely P gets turned into a whiskering on the left and Q gets turned into whiskering on the right, and here the other way. Except P gets turned into whiskering on the right and Q gets turned into whiskering on the left. And now why does this commute? Well, here is where our earlier work comes in. So this thing, these naturality terms are defined by induction on P and Q. So in particular, if P and Q are loops, and they are in our setting, these terms are not going to compute to anything. So that's why we go to an earlier slide where we remember that the terms, the naturality terms in the case when one of the paths is 1, here and here, are actually explicitly described in terms of, getting rid of the whiskering and then introducing the whiskering again. And if we go to the diagram, this is precisely what we have here, right? So basically, if we replace this term by the analogous explicit description of the naturality, then that is exactly what is going on here, right? Like we turn the whiskering into P, and then we turn it into whiskering again, and the same thing over here. And let me just point out that the reason why the way we prove this is actually, it requires a little bit of effort, because we would like to somehow prove this by, I'm sorry, shut up. Oh, sorry, it's my cat's dinner time. So, yeah, where was I? Oh, yeah, I was saying the way we prove this is that in the naturality, so if we're talking about the naturality of Eckmann-Hilton, then we would like to prove it by induction on Q, for example, in this case, and induction on P in this case. But we can't do that outright, because P and Q are loops. So we would like to free at least one endpoint. And let's say we free this lower one. So as soon as we, however, free one endpoint, let's say we replace this one by, I don't know, some Y, then that would allow us to actually do induction on Q. However, this thing would no longer be an identity. This would be, you know, getting rid of the concatenation and then reintroducing the concatenation. And now this path here would be Y. But we remember that this is precisely the explicit characterization of the Eckmann-Hilton term when one of them is, when the path on the right is reflexivity. So actually that's why we have this slide over here, slide number 12, that allows us to actually prove that indeed, in the case when we generalize one of the paths, then what we get here is not going to be definitionally equal, but it's going to be propositionally equal to the Eckmann-Hilton term when the other path is reflexivity. So we are now here. Actually, we're even further. We're here. Okay. So now we proved pretty easily that this triangle actually commutes, and so does this triangle. So the question is, are we done? Well, basically we're done, because we have proved that the whole diagram commutes modulo having this little path in here that was a 1. But since that's a 1, that's not really a big deal, right? And in fact, if we go to the COC code that Steve asked about, the only thing that we do there is we basically get rid of the 1 in one simple lemma. And that's basically it. And the whole thing can be proved in, as you can see, like 273 lines, but I'm also redoing a bunch of stuff there. So that probably can be, that probably already exists in the library. Okay, so that's a very simple proof of Syllepsis from me. And this was supposed to take an hour, but unfortunately the proof is just so short that I'm basically done at this point. And the question is where to go from here. So obviously, the idea that people had is that we can somehow use the Syllepsis term to compute the Bruneri number in some less, in a way that imposes less torture on the reader and the person coming up with the proof, and the person who's supposed to formalize it. And then somehow more open-ended goal is to use some of these techniques to perhaps attack some other problems in synthetic homotopy theory. And I'm actually compiling a list of further suggestions. So I'm hoping that some other people have some more suggestions for open problems that perhaps I could work on from now on. Thank you, Carl.
Okay, thank you. Let's silently thank the speaker. Right, and then, so like she said, we have a lot of time, but maybe we'll open it up to questions, but also, I mean, maybe you want to tour us through the COC file as well.
Yes.
But anyway, people can, if anyone has a question,
Yeah.
now is a good time.
So I would actually like to hear from Egbert, if he's still here, how he thinks this relates to his proof. But yeah, any other questions too, you know.
how it relates to my proof. My coherence diagrams were much more complicated than yours. So you really managed to bring it down to the essence, and it's really, I think it's really beautiful how you do it. I cannot say mine was much more complicated, and also that's why I didn't manage to formalize it yet, and you just do it in less than 300 lines of code. So.
Do you think there's some overlap in the argument?
Some overlap. Well, it's about the same topic.
Oh, okay.
I'm sorry. Is there some overlap?
In the reasoning, yeah, like it.
What did I do? Maybe I'll come back to it after you.
Okay, yeah.
I have to think about it.
Okay.
Well, this slide is up. I have a question.
Yes.
So the first point there about the relation to pi4 of S3, has anyone formalized the fact that this does give a generator of pi4 of S3? As it's phrased, there's no spheres mentioned anywhere. So is there a way to see precisely the connection to pi4 of S3?
I think that this has been proved. Namely, I know it from Noah Snyder, but I don't know if he actually formalized it.
Yeah. So then regarding the third point about suggestions for things to do.
It's to do this. To do this, yes.
Right. I mean, it would be really interesting to actually know for sure that from the Freudenthal suspension theorem, we know we get a generator of pi4 of S3, and that it's equal to one of the terms that comes up here, and then that you're proving that it's got order 2, well, order at most 2.
Yeah.
So the other thing would be to prove that it's not already a trivial path or a trivial loop.
Okay.
I think those things would be really interesting to do.
So what is the, yeah, go ahead.
I just wanted to add another suggestion, since we were adding to the suggestions. Since your method is so efficient and clean, maybe you can even use it to prove the next coherence. If you look in the for loops, what goes on between the Syllepsis, I think it should be order 2 again. It's not so sure.
Oh, okay. So go.
You can just keep going, no? And your method is so you managed to reduce everything just to a simple path induction. So maybe you can get something quite easily.
So would that be actually useful for some specific problem?
I don't know.
That we have in mind?
5 of S3.
Okay. Oh, okay. So you think that basically is the same sort of principle, just one level up?
I would think so.
Okay. And so I have a question for the people familiar with the proof or the intended proof of pi4 of S3. So what are the missing pieces there? So we have the Freudenthal suspension theorem, then now we have the Syllepsis, and so what else remains to be done? I mean, apart from proving that this is actually a generator, would that sort of?
Well, proving that it's a generator and that it's not already trivial, I think, are the 2 steps.
Okay, so that's the crucial thing. And then I am not actually familiar with Guillaume's version of the proof. So how different is it? Because I don't think he used, any kind of argument like this. So do we know?
It's completely different. Yeah. I don't see any connection.
Yeah, so I think he uses a lot of, like algebraic topology machinery there, which is why I was largely kind of lost when I try to follow the proof. So I kind of like this approach because it seems very, very simple. Like I don't have to actually know anything to do it. So, okay, so are there some more questions, or as Carlos suggested, we could go over the code and Steve can go get lunch? Okay. Okay, so
I'll ask one more question before you start doing the code, and that is, what does the classical proof of this look like? What goes into a classical proof of Syllepsis?
see, that's the thing. I don't actually know because Egbert, is that what you were actually doing? I have
No.
no idea how to prove it in the.
Just look at what is asked and the structure of the coherence diagrams that naturally come up, and mine came out more complicated than yours, but I was also just looking at the nature of the problem, not at the classical.
So you were not actually following the mathematical geometrical proof.
Okay. Well,
Uh-huh.
I can look it up myself. I thought
Okay.
there must be a classical proof. I don't know who did it first or what kinds of methods are involved. I was just curious about that, but I'll just Google it and I'll find out.
But so this is something that Jamie was talking about actually in that talk, I think, but he wasn't. I don't recall the particulars.
Okay, thanks.
Mm-hmm.
It's nice to see your approach. I want to call it a naive approach, not in a pejorative sense, but just
right. Yeah, definitely.
Looking at the type theory or the algebra, the path algebra there, and cranking it out. It's great that works.
Yeah, so that's why I'm sort of wondering if there are other problems of this nature that basically can be done completely naively without knowing anything about, how it's done geometrically and all that kind of stuff. So I'm gonna look into the proving that it's actually a generator, so that it's not a trivial path. Okay, so now
maybe just let me interject really quickly that it was so Jamie Vickery gave a talk in December 2020 at HoTT, where he was talking about this sort of restricted sort of like a diagram calculus for strictly unitable infinity categories. And I think one of the examples he was talking about was Syllepsis there. So it's not hot, but just sort of a type theory that's only for drawing these sort of diagrams. And all the diagrams you can draw there correspond to, coherences that will hold in in some kind of infinity category.
So do you remember the counterexample he gave to prove that Syllepsis actually doesn't hold one dimension lower?
I'm not sure.
I think it was due to him, but oh yeah. So maybe now I'm gonna point out where we actually. Well, I mean, I guess it's obvious, but we use it here when we have the mismatching endpoints, and we insert the Eckmann-Hilton term there. So there we go one dimension lower. So we need to know that the Eckmann-Hilton term actually exists. So that's why the proof would break if we were just to do it for 2 loops instead of 3 loops. So that's where we need it. Okay, so maybe now I can go quickly through the code for interested people. So, okay, so I think, is this kind of, can people see this? Or should I zoom even? Okay, so, yeah, so,
maybe you can
this
hide
is
the thing at the bottom again.
okay, like this. Yeah. Okay.
Yep.
Yeah. So here the C. I'm really bad with names. So if somebody can suggest something better, that would be great. So this C is just the whiskering. I'm gonna go through. I'm gonna go to the beginning of the slides since I largely formalized it in the way that it's done here. Okay, so whiskering exists in the library. So then we have the Whiskering Exchange Law, which is the C here. Okay, then we have the naturality of the concatenation on the left and on the right. And here we have the thing I called the double arrows. Yeah, that basically just gets rid of the spurious ones. And then we have a similar thing that gets rid of the spurious ones on the other side. Okay, and then we have this section that can probably be, yeah, that's about gluing two squares together. So I think that should be largely, yeah, okay, so that's largely inherited from the wildcats. So this part was, okay, so then we have square inverse, where I kind of want to revert the order in which the vertical paths go. So that is again, yeah, as I said, I was doing kind of from scratch, but this should already exist in the library. Okay, so now this crefl L thing is, if we go here, so here when I was arguing that the Eckmann-Hilton proof is this basically trivial thing when one of the paths is an identity, then I mentioned something about the whiskering basically being also sort of trivial when one of the paths is an identity. So that's sort of what this says. It says that the exchange law, if like the left path is just an identity, then basically it just corresponds to reintroducing, getting rid of one and reintroducing it on the other side. And here we have something similar. So again, I'm not sure if something like this already exists in the library or not. Here we have the Eckmann-Hilton proof, which is just the first part, which is the parallel composition. Then we have the exchange law, the Whiskering Exchange Law, and then again we do the parallel composition in the other direction. So now we have something that I sort of wanted to refactor a little bit, but yes, so let me, okay, so this basically, now when we go here, we have something that corresponds to the first property of Eckmann-Hilton, namely that it's actually this sort of trivial thing when one of the paths is reflexivity. So that's what we're proving here. And we did it by introducing some sort of generalizations. So that's what this guy and that guy are for. So basically we suitably generalize the thing and then we apply path induction. Okay, so then these other guys, the EH nat L and EH nat R, correspond exactly to the naturality of Eckmann-Hilton. So we, yes, so here we actually define the naturality. The nat2 squares lemmas actually state what we have, okay, actually state what we observed on these slides, that we can express the naturality as 2 squares, is the name. Oh, where are we? In the code. Okay, yeah, so this explicitly characterizes the naturality. And now we are doing the diagram. So S stands for square. And here I am actually proving that the square commutes. So where is the, oh yeah. So here we are basically this we already did. Oh, okay. Oh, wait, here, that was here. Okay, so here, the commutativity of this square corresponds exactly to this, where the DL and DR are, I forgot why I named it that way, but anyways, yeah, so these are the two edges that we constructed by means of the two squares. Hence, we see that they're defined as these two composition of two squares. So then this proves that the square commutes. So as we can see, induction P, induction Q, and then just something obvious. And then, so then we basically have that this square commutes. And then what we do is we're proving that the triangles commute. So that finishes step one. And now step two is proving that these triangles commute. So here, yeah, so again, we use suitable generalization. That's what the F is for. That basically generalizes the EL, so whisker. Yeah, okay, so, right, okay, so those are here, that's the explicit characterization. Now here we have the abstraction that proves that, yes, so here if we look at the conclusion of this lemma, then it says that the two squares, that the two squares characterization that we have here is actually the same as the composition. This is the first guy like this, and here's the second guy like this. So this proves that the triangle commutes. And then, okay, and then basically here, the H here just turns the diagram that has this extra one, as I mentioned, into the actual proof of Syllepsis. So that would be, yes, and this guy just says that, these two guys say that we can replace the natural, the edge defined by naturality by the edge defined explicitly as in terms of the whiskerings. Okay, so it would be great if somebody had better suggestions for how to refactor this code, because I think that there are places where I can use some existing stuff from the library, and currently it's not particularly illuminating what's going on there. So, okay, that's about it from me.
Okay, I'll maybe read it out loud. There's a long message in the chat from Axel, who says, who's talking about some work that I think he and Anders Mortberg and maybe some others have been doing in cubical agda. Says, concerning Brunery's proof, we are getting a bit closer to a full formalization over in the cubical library. We have pretty much all of chapter 6 and most of his results on cohomology. I'm not really sure about how the Syllepsis is supposed to give pi 4s3 is Z2, but at least what we have so far should be relevant to proving that pi 4s3 is non-trivial, which I guess would be needed even if you use the Syllepsis. And yeah, I think that's right.
Yeah, yeah. It is.
And we also have a cubical proof of the Syllepsis, and here's a link to GitHub. I think it's pretty similar to Kristina's proof, albeit very cubical. Just thought I'd let you know in case someone wants to try to use it for computations. So I did take a look at his link, which is also in the chat. And yes, I think it, where did I lost my tab. Right, well, it's hard to eyeball, but it seems kind of like it's, yeah, it has some complicated filling problems that are, you know, pushing.
Can I look at the, I don't see the chat, so I don't see the link, but I would be interested in, wait, where is the chat? Okay, can I stop sharing my screen?
Yeah,
I think so.
Yep.
Okay, and now I want to try to find.
I would offer to
chat.
send you the link in the chat, but I don't think that will help.
I see it. Okay, yeah. We have a cubical proof. Okay, yeah, so now I see that's an AGDA. Okay.
Yeah, it's
so
in cubical AGDA. Yeah. So I was going to ask the sort of, you know, I'm contractually obligated to ask, you know, would cubical type theory make this proof easier? And I think the answer is not especially, right? I mean, it's the sort of things that cubical type theory make easier are not this sort of, you know, path algebra. It's more like things like app. So yeah, and indeed these, you know, the fillers, if you can see the proof now, are, you know, it's, I don't know that it's, yeah, I think it's maybe, not simpler than what you're doing.
Yeah. So I think that my impression is from this proof that I guess and if somebody looks at the code, then the majority of the work is actually stating the lemmas that we're proving, and then the actual proofs are just like a couple lines of induction. So yeah, I agree with you. I don't really think that moving to the cubical setting would simplify much.
Right. Well, maybe before we get too far into the weeds, are there any other questions? And then of course we can continue to discuss, but I want to let people ask any sort of other questions they might have. Okay, well, I think maybe let's thank the speaker again.
Thank you.